Hi guys, it's Mrs. Webb here again. I'm coming to you today to talk about net ionic equations, which I think once you get the hang of them, you'll find them really quite repetitive in nature and fairly simple so long as you understand your original solution equations, right? Your dissociation equations and your ionization equations specifically. So what a net ionic equation is it shows what is taking place when a chemical reaction that happens in solution occurs. So something like a single replacement reaction or a double replacement reaction. We've always written our balanced chemical equation and we show the reactants and we show the products, and then we balance and that's it. With a net ionic equation, what we do is we look at specifically what is happening to those species in solution, and why is it that they are forming brand new products, right? And so they're used to determine the parts of the reaction that are actively involved in producing the products. Okay, so actively involved. Because even though specific species or ions may be in solution, they may not necessarily be active in the reaction, right? And those ones that are not active in the reaction, those are the ones that we call the spectator ions. So you can kind of think of it like going to some sort of an event, and the people that are putting on the event, they're actively involved in setting the stage for you, basically. They're actively involved in entertaining you for a period of time. The people that are, buying their ticket and going to the facility that's hosting this event, those are the people that they're partaking in it, they're watching it, they're enjoying it, but they're not actually actively involved in making the process take place. They're just spectating, right? And it's not to take away from the spectator ions. We're just identifying the parts of the solution that are actively driving the solution forward. Okay, so there's a couple of rules that we're going to follow when we do these net ionic equations. Okay, and the rules are this. The first thing you need to do whenever you're being asked about spectator ions or net ionic equations is you're going to write your balanced chemical reaction. That's the first thing. So we're writing balanced chemical equations. The second thing is you're going to look for what are the high solubility species in that chemical equation. So that could be high solubility ionic compounds. It could be strong acids. So those acids that are above the gray line on your acid table. And you're going to show what happens to those high solubility ionic compounds or those strong acids when we put them into solution. And specifically for this, just to help you guys out a little bit here, specifically for this, when we talk high solubility, what you're looking for is species with aqueous subscripts. The ones that have, and I'll put this just kind of as an aside for you, solid, liquid, gas, these are all considered low solubility. And if you remember on one of the first lessons we did when we talked about substances that were low solubility in solution, we said that when we put those substances into water, they remain as is. Their chemical formula doesn't change, and their subscript remains as is. It does not become aqueous. So specifically, we're looking for those species that are high solubility with an aqueous attached to them. And in terms of strong acids, what we're looking for is those acids above the gray line on your acid table, right? So your acid table in the data booklet. Because that's specifically what you're looking for. Now, once you do that, you're going to ionize or dissociate all of those high solubility substances. And what you're going to notice when you do that is that you have some substances that are repeated on the reactant side and on the product side. And when you notice that those substances are repeated on the reactants and on the products, what you're going to do is you're going to cancel them out. Okay, so you're going to cancel out identical entities that appear on both reactant and product sides. And whatever is left over, that is going to be your net ionic equation. That's going to show you what is actively driving the reaction forward. Okay. So I'm going to show you an example because it's hard to kind of visualize what's happening when you see the rules, but I'd like you to, when you're doing these practice problems, I'd like you to have the rules nearby so that you really kind of internalize the rules and you get into the habit of following the step by step, right? The more you practice that, the easier these questions are going to be. They're very, very similar in nature. There's very little ways to change this up or give you a something that'll surprise you in terms of questions. They're pretty standard questions. So I've got an example for you down here. And it says a student mixes a solution of lead 2 nitrate and sodium iodide, and they observe the formation of a bright yellow precipitate. Another student recorded the same observations after mixing lead 2 acetate and magnesium iodide. Explain how this is possible. Okay, so this one's a little bit of a weird, I guess, setup for the question because it's not really asking you for net ionic equations, but what we need to do is we need to write the net ionic equations to see why is this precipitate forming in these 2 separate chemical reactions. Okay, so the very first thing we do is we write our balanced chemical equation. And a lot of times you will see this, as abbreviated as balanced chemical equation, BCE. So if you see that, that's what that means. So for the first reaction, we've got lead 2 nitrate, which is PbNO3 we know that this is in solution, so aqueous. And we know that this is in solution, I believe it told us in, yes, at the beginning, the student mixed solutions, right? So we know it's aqueous. And they mixed sodium iodide in solution, and it produced lead 2 iodide and sodium nitrate. Now, to figure out what the states of matter are here, we need to go to our solubility table. If you go there, you'll notice that when iodine bonds with lead 2+, it forms a solid. And then sodium nitrate forms an aqueous solution. So step 2 is we're going to look for all of our high solubility ionic compounds. Anything that has this aqueous subscript attached to it. And everything that has an aqueous subscript attached to it, what we're going to do is we're going to dissociate it or ionize it. In this case, we don't have any acid, so we're going to dissociate everything. Because when I put this lead 2 nitrate into my solution, we know already that because it's high solubility, this is going to dissociate into its ions. And so is the sodium iodide, and so is the sodium nitrate. So what we do in our total ionic equation, which is step 2, is we're going to dissociate this. And sometimes it helps to see what's happening here. What color do I want? I'm feeling indecisive. Let's go with this one. No, let's go with this one. So sometimes it helps to see what's happening here. We're dissociating this into its two ions. So you're not writing the solution equation in its entirety. You're basically saying these are the products of what happens when I put my lead nitrate into solution. I'm just showing the products. And then I'm going to do the same thing with my sodium iodide. So I'm going to break my sodium iodide into the products. Okay. Lead 2 iodide, remember that when we put this into solution, it remains lead 2 iodide. So it stays together. We do not dissociate this because it's low solubility. And then for the second part, our sodium nitrate will also dissociate. Okay. So this is essentially all of those the examples that we did on one of the first lessons of the solutions unit. We were writing dissociation equations, ionization equations, low solubility equations. This is essentially what you're doing in step 2. The only difference is that instead of writing the entire equation, we're listing the products in the chemical reaction, right? So we're listing the products of this dissociation equation plus the products of this dissociation equation. And as a result of these ions floating in solution, we're arriving with a brand new product in this chemical reaction. Okay. Now remember, when we dissociate, we'll have some ions that are duplicated. And so if you notice, we've got 2 nitrate ions on the reactant side, and we've got 2 nitrate ions on the product side. We've got 2 sodium ions on the reactant side and 2 sodium ions on the product side. So what we do is we cancel those out because they're repeated. And the only thing that's left over is my lead 2 plus aqueous plus my 2 iodine minus aqueous, and that's going to give me my lead 2 iodide solid. So this final step, that's my net ionic equation. What's actually driving the reaction forward is the lead ions and the iodide ions. That's why this lead 2 iodide precipitate is forming. And the spectator ions, the ones that are in the solution but they're not actively participating, those are the nitrate and the sodium ions. Okay, they didn't drive the reaction forward. They're just observing. They're in there, but they're observing. Okay, so that's essentially a net ionic equation. Usually the question I get at this point is, well, what happens if we get, let's say, 2 nitrate ions here and only 1 on the product side? Does that mean I would have 1 nitrate ion left over in my net ionic equation? Well, if you think about it, and you think about our conservation, our law of conservation of mass, right? When we balance a chemical reaction, we've said that the reason we have to balance our chemical reaction is so that the number of atoms are equal on both sides of the reaction, and the mass is equal on both sides of the reaction. And remember, mass, because your atoms carry mass. They carry a certain mass associated with them. So if you make the number of atoms on either side equal, you're going to make the mass on either side equal. So those two things have to be conserved. Now, if you're balancing the number of atoms, there's no way for you to end up with different numbers of atoms or polyatomic, of ions or polyatomic ions on the reactant side and on the product side, right? If I end up with 2 sodiums on this side, on the reactant side, and only 1 on the product side, that means that I have messed up my balancing in the first step. So if that happens, you need to go back to this first step and you need to have a look and see, where did I mess up the balancing of the chemical reaction? Something's not balanced. This step here, the total ionic equation, everything should be balanced, right? We should have the same number of everything on both sides. So I've got 1 lead, I've got 1 lead. I've got 2 iodines, I've got 2 iodines. 2 sodiums, 2 sodiums. 2 nitrates, 2 nitrates. So we're balanced. Okay, so that's the first part. Now for the second part, we're going to redo this net ionic equation, but we're going to redo it for that second reaction. So we've got lead 2 acetate in solution. It reacts with magnesium iodide in solution. It produces lead 2 iodide solid and magnesium acetate in solution. So remember, for the products here, I need to look at my solubility table to see what the states of matter are. So I've written my balanced chemical equation. I've looked on my solubility table for the products, and now I look to see what are my high solubility substances. Anything with an aqueous. And of those high solubility substances, what I'm going to do is I'm going to dissociate and I'm going to ionize the high solubility substances. So my lead 2 acetate is going to dissociate into its parts, into its ions. My sodium iodide is going to dissociate into its ions. And my magnesium acetate is going to dissociate into its ions. Lead 2 iodide solid is low solubility. So let's write that in. Low solubility. So it stays as is. Okay, so it stays lead 2 iodide. It does not dissociate, right? This is a low solubility equation. Now, what we do is we have a look to see. Obviously, some stuff is going to be repetitive, so we look to see what are the ions that are repeated on the reactant side and on the product side. And if I look, I have 2 acetate ions here. On the product side, I've got 2 acetate ions. Those can cancel out because they're repeated. I've got 1 magnesium ion on the reactant side, and I have 1 magnesium ion on the product side. So those are repeated, and we can cancel them out. Those are my spectator ions. They're the ones that are in the solution, but they're not actively participating. They're not actively driving the reaction forward. What's left over is my lead 2 plus, my 2 iodides, and my lead 2 iodide solid. That's my net ionic equation. Okay. So the reason these 2 separate students observe the exact same thing is because the net ionic equation in both reactions is identical. In both reactions, it's the lead 2 plus and the iodide ion that are driving the reaction forward. And so that's why we're observing the precipitate in both reactions. Okay, so that's one example. I've got a single replacement example for you here to have a look at. So this one says, write the net ionic equation. Generally, your questions will be formatted like this. Write the net ionic equation for the reaction of zinc metal and aqueous copper 2 sulfate. Okay. So remember, first step, balanced chemical equation. So we've got zinc solid, zinc metal. It's reacting with copper 2 sulfate aqueous. It's a single replacement reaction. So the cation is going, or the metal is going to swap places with the metal. The copper will precipitate out and will form zinc sulfate. And so I look to see on my solubility table and I find that zinc sulfate is aqueous. We check to see are we balanced, and yes we are, so we can move on to step 2, the total ionic equation. So here we're looking for what are our high solubility substances. Well, I've got 2 solutions that are aqueous. Everything else is low solubility. So if zinc is a solid, it stays zinc. Lots of students will add a charge to my zinc, right? Remember, a low solubility solution or a low solubility substance does not change. It stays as it is in the balanced chemical equation, or as it is on the reactant side of the solution, or on the left-hand side of the solution equation. So zinc stays solid. There's no charge here, so don't put charges there. The copper 2 sulfate, because it's aqueous, high solubility, it's going to dissociate into copper 2 plus aqueous and sulfate 2 minus aqueous. My copper solid remains copper solid. Again, there's no charges. Students love to put charges at this point. They're charge happy. They love to put charges on everything. If it has a solid, It does not carry a charge. And then my zinc sulfate will dissociate into zinc 2 plus aqueous and sulfate 2 minus aqueous. So that's my balanced, or my total ionic equation. If I've done everything right, I should have, potentially, not always, but I should have duplicates. I look to see I've got one sulfate here and one sulfate here. And I've got equal numbers of everything, which means I balanced correctly in step one. So the leftover equation, the net ionic equation, is going to be zinc solid plus copper 2 plus aqueous gives us zinc 2 plus aqueous plus copper solid. That's the net ionic equation for this particular reaction. That's what's driving the reaction forward. The fact that we start with solid zinc and we end up with zinc ions in solution. The fact that we have copper 2 plus ions and we end up with solid copper in solution. Okay, or precipitated copper. That's what's driving it forward. Now, if the question doesn't tell you to state your spectator ions, I don't think it's necessary. You know, usually it'll say state your spectator ions. If you want to state the spectator ions, by all means, please do. In some very small instances, I alluded to the fact that usually we'll see ions that are repeated. In some instances, we may not see ions repeated, and in that case, your total ionic equation is actually your net ionic equation. So sometimes you'll find that you end up stopping right there at the total ionic equation because you can't cancel anything out. And it's not that you've done anything wrong, it's just that all of the ions are actively participating. The other thing I wanted to also point out is that the reason I didn't cancel out the zincs or copper is because notice that this is copper solid with no charge, and this is copper 2 plus. So those are two separate entities. So that's why they can't cancel out. The other one I wanted to do is I wanted to do an acid example. And so we got write the net ionic equation for HCl and barium hydroxide in solution. So step one is we write our balanced chemical equation. Okay, so we've written it out, we balance it. Notice that I produce water liquid, not aqueous. And remember that anything that is liquid, solid, or gas, that's considered low solubility. So those will not dissociate or ionize in solution, they'll remain as is. Because I'm dealing with acids here, I'm going to ionize the acid, so I'll produce 2 hydrogen ions, aqueous, plus 2 Cl minus aqueous. I'll dissociate my base to barium 2 plus aqueous, plus 2 hydroxide aqueous. I'll dissociate my salt into barium 2 plus aqueous and 2 chloride ions aqueous, and my water will stay as 2H2O liquid because it's low solubility. And if you notice, I have duplicates. My chloride ions, my barium ions, they all duplicate. So we're going to cancel them out. They are the spectators. And I end up having 2 hydrogen ions plus 2 hydroxide ions plus 2 waters. I'm going to take this to the lowest common denominator. So it means I've got a hydrogen ion plus a hydroxide ion plus a water being produced. So that's my net ionic equation. The reason a base, a strong base and a strong acid will neutralize each other is because the net ionic equation, what's actually driving the reaction forward, is the fact that these hydrogen ions and these hydroxide ions are forming water. That's what's actively driving the reaction forward. I'll show you this example too. I believe, there we go. We've got H2SO4, again, another strong acid reacting with magnesium solid. So remember, acids, when they react with active metals, will produce hydrogen gas. So we write our balanced chemical reaction, and I get hydrogen gas being produced. My sulfuric acid is going to ionize into 2 hydrogen ions plus a sulfate ion. The magnesium is low solubility, so it remains magnesium with no charge. The magnesium sulfate dissociates into magnesium ion and sulfate ion. And then my hydrogen gas remains hydrogen gas because it's low solubility. The sulfate ions are duplicates, so they cancel out, they are spectators. And then this tells me that the reason I am, or what's actually driving the reaction forward, are my hydrogen ions in solution, the magnesium solid, producing magnesium ions and hydrogen gas. So that's the net ionic equation here. And last example here, write the net ionic equation for magnesium chloride with copper 2 sulfate. So again, we write our balanced chemical equation. Everything except for the copper 2 chloride is going to dissociate. So we get magnesium ions, chloride ions, copper ions, sulfate ions. This produces 2 copper 2 chloride, solid, and then the magnesium sulfate dissociates. We look at our duplicates, cancel them out, and then you'll notice that we end up with 2 chloride ions plus 2 copper 1 ions, 1 plus ions, to produce copper 1 chloride. Notice that these are all divisible by each other, so we take it to the lowest common denominator. Okay. So that's net ionic equations, guys. I think you've had a good look at some examples here. We'll give these a practice in class if you've got